Hello, today I'm here to talk to you about how you can use LiveRecorder Observatory from Undo to analyse and diagnose a real-world issue detected in SQLite. As you can see, the integrity check indicates that the database disk image is malformed. This issue was detected back in 2019 with the version 3.30.0 release of SQLite. The ticket contains a number of SQL commands which are issued prior to running the integrity check, which ultimately reports the error. Here we have an example issue in our GitHub system, which has all of the necessary instructions to reproduce and record this error. The recording, as well as the original sources, have been registered with Observatory so that you can use the link to debug in your browser. As VS Code is loading, we can see the log of the session where we generated the recording. You can see the command used to generate the recording, as well as the database disk images malformed error that was produced. We also have an SQL file containing the commands used to reproduce the issue. Now the recording has finished loading and we are at the end of recorded history. As SQLite terminated normally, we're in the standard library exit function and we don't have the source code for this, but we don't need it. As the error happened when the integrity check was run, let's see if we can find that in our source code. SQLite is packaged such that the majority of code is in shell.c and SQLite 3.c. Let's check shell.c first. No luck, so let's try SQLite 3.c. This looks more promising. Since this was a string in the original command, let's see if we can match it as a string. The first of the two matches is just before an integrity check function, so let's put a breakpoint on that. And there's a second integrity check function, so we'll put a breakpoint there as well, and we'll see which one we hit. As we're currently at the end of the recording, we can use reverse continue to run backwards, and we should stop at one of these breakpoints. And we have stopped at one of the integrity check functions. Let's step over it and see what the return value was to make sure it returned the error. And the return code was 267, but it looks like these return values are enums, so let's peek at the definition of one of them to try and work out what they mean. We can see that the value 11 means the database disk image is malformed, which would make sense as 267 is 11 plus 256. So let's scroll down a bit further and see if we can find out what bit 8 being set means. So 267 is a corrupt vtab. So let's step back into this function and see if we can see where the error was detected. It looks like RC was set 2 lines above, so let's step back and confirm that. And it was, so let's undo that last reverse next, and we can step back into the function to see where it was returned. And we need to step back again, and here we are. So it's coming from the data structure pointed to by P. And P-RC is currently 0, so let's step back a couple of times so when it still had the error value there. And now we can use the last command, which is able to run the recording backwards to the last time a specific expression was modified. So here we are where the error was actually detected. If we have a look at the locals, we can see the IOF and N byte value. That's 4 and 11. And let's have a look at the pleaf-sz leaf value. It's 11, and 15 is greater than 11, and that's where the errors come from. So let's have a look at where these values come from. First, IOF and N byte. IOF is presumably an offset into a block of data, and the FTS5 get varint32 appears to be a function for reading a packed variable width integer from the data stream. So let's have a look at what the pleaf-sz leaf means. Let's check its type definition to see if it gives us any hints as to the values it's supposed to contain. So this looks like it's got a pointer to a block of data, an NN value, which is the size of the data in bytes, and sz leaf is the size of the leaf without page index. I assume the page index is some sort of header or metadata which shouldn't take up a substantial part of the block. Interestingly, looking at the values we have, 65,568 and 11, it seems like that 11 is erroneous, as we already saw that the offset was 4, and it's quite plausible you got metadata as well, so a size of 11 seems especially small to contain everything apart from the page index. So let's use last again to this time see when this sz leaf value was set. So it seems to be set when FTS5 get U16 reads an unsigned 16-bit integer from the address passed. Let's have a look at that address and see what's there. Actually, let's have a look at multiple bytes of that address and see what's there. So the first 2 bytes are 0 and 11, which from an unsigned int would be the return value. So let's see where that 11 came from. Again, we can use last. In order to track back past this memcopy, we need to find out where that 11 was located in the original source buffer. To do this, we can use the address of the watch point as well as the pointer to the destination buffer to work out the offset from the start of the buffers. And then using that offset, we can combine that with the pointer to the source buffer in order to work out where that 11 was and go back to when it was written. And we've hit another memcopy. The good news is that the old value of 11 means that we had the right offset. So let's repeat what we did and see if we can go back to before this one. And yet another memcopy, so same again. And one more time, hopefully not much further for this. And finally we've got to the point where this value was stored. We seem to be in the FTS5 put U16, so we're storing the U16 value. Let's do a quick reverse finish to see where this was called. So we're storing ppageBuff.n. Let's have a look at what that value is. And we found where our data corruption is happening. 65,547 is not a value you can store in a U16, and therefore it is being truncated to 11. This may be the source of the corruption, but it should never have been allowed to happen. Let's use last to go back and see when this value 65,547 was actually stored, and here the value was changed from 59,000, which would have been fine in a U16, to 65,547, which is where the problem comes. If we look a little above this, it looks like the value was checked against the PGSZ value and was deemed to be sufficiently small to fit. This is clearly a problem. Let's see what that value is and where it came from. So the 70,000 value came from a configuration structure. Let's go back and check that. And here we see the 70,000 value being set. It appears it was range checked between 0 and FTS5 max page size. And FTS5 max page size is set to 128k. This is a fundamental problem when your data structure relies on unsigned 16-bit offsets, so this clearly needs to be changed from 128k to 64k. If we go back to the original issue, we can see in the timeline that there was a check-in for this. And we can see that we did indeed identify the correct code change needed to resolve this original issue. Hopefully this has been informative for you to see how you can use time travel debugging in order to tackle issues such as this, using reversed operations including last to track back the symptoms to their causes and ultimately find the root cause of the issue. Thank you for your time.